Now I'd like to introduce you to our second keynote speaker this morning, Daniel Lidar, who is Professor of Engineering at the University of Southern California. He holds joint appointments in chemistry and physics, and prior to joining USC in 2005, he was a faculty member at the University of Toronto. His main research interest is quantum information processing, and he's the director of the USC Center for Quantum Information Science and Technology, and the scientific director of the USC Lockheed Martin Center for Quantum Computing. Professor Lidar is a recipient of a Sloan Research Fellowship, a Guggenheim Foundation Fellowship, and is a fellow of the AAAS, APS, and IEEE. Please join me in welcoming to the stage Professor Lidar.
Thank you. Good morning, everyone. It's really a great pleasure and an honor to be here. That was a younger picture of me. Now I have some gray hair. But I'd like to tell you about the impact of quantum computing, which of course is a huge topic, and I will not be able to do it justice, but I hope to give you a glimpse into what's going on. So since I'm an academic, I thought I'd start with a little bit of history. It's well known that quantum computing started with Richard Feynman, the famous physicist, who wrote a seminal paper back in 1981, where he talked about simulating physics with computers, and that gave him the credit for starting the field of quantum computing. However, it's less well known that this might be the first instance of, depending on your perspective, either Russian meddling or fake news, because there was a Russian mathematician who's still alive and is actually a very eminent mathematician, Yuri Manin, who in fact proposed quantum computers a couple years before Feynman, but unfortunately for him it was in a radio broadcast on Radio Moscow, and his words were therefore not immortalized as well as Feynman's. Feynman started his paper, strangely perhaps, not by talking about computation, but by noting that he didn't know what a keynote speech is. So this is one of those rare cases where I can say that I know a little bit more than Feynman, but only because I read his speech. And so let me give you the outline of this talk. I'd like to start by providing a little bit of background on what quantum computing is, and then plant some seeds for the panel discussions that are going to follow. And then I'd like to speculate about where the field is going in the next 5 years or so, or perhaps beyond. So what is it that Feynman actually said that gave him the credit? Well, his observation was that it's hard to simulate quantum mechanics itself. And he said, why don't we let the computer itself be built out of quantum mechanical elements which obey quantum mechanical laws in order to simulate quantum mechanics. So that was his interest in this seminal work. He was interested in what we now call quantum simulation, which is using quantum computers to simulate other quantum systems. And that's a very important theme, which I'll get back to a little bit later. So why else is quantum computing interesting? Of course, we heard a lot about it in the previous talk. Here's one reason. It's the inevitability reason. I'm sure most of you are familiar with this type of chart. It's a depiction of Moore's law and Dennard's law, or Dennard scaling. This is the number of transistors in powers of 10 in thousands as a function of time, and what you're seeing here is 45 years worth of data going from the early 1970s all the way to 2015. And we can see that Moore's law is still going strong. We have exponential growth in the number of transistors per chip, but Dennard scaling is coming to an end. Dennard scaling is concerned with performance metrics such as single thread performance, frequency, typical power drawn. These are all flattening out. And the response of computer engineers has been to increase the number of logical cores, which, as you can see, is actually growing exponentially. Now, this is a type of parallelism that is built into the hardware, and the more logical cores, the more expensive it is, of course. And in fact, this kind of parallelism is what we're going to get for free, in some sense, from quantum mechanics. But the really interesting thing about this chart, in my opinion, and many others, is what I like to call the wall of too small. So when exactly this is going to happen, we don't know, but I think it's a fair prediction it's going to happen before 2020. The radius of a silicon atom is only 0.2 nanometers, and the current Ivy Bridge processors in the Intel chips at 22 nanometers, each transistor, is about 100 atoms wide. That's not very big. Now, the 11 nanometer transistor is on Intel's roadmap, and that will only be 50 atoms wide. The dielectric thickness is only 6 atoms. So it's obvious that we are at the atomic scale, and we're approaching the scale at which quantum effects are going to be inevitable. And that, too, was anticipated by Feynman. He wrote, or said in one of his speeches, "It seems that the laws of physics present no barrier to reducing the size of computers until bits are the size of atoms and quantum behavior holds sway." And this is a big concern for computer design nowadays. But from the perspective of quantum computing, that naturally operate at the atomic scale, this is an opportunity. They offer us a path beyond inert scaling and a lot more. So what more is it that quantum computers offer us? Well, most famously, they offer us amazing speedups, algorithmic speedups. When we compute using quantum laws, as Shor most famously showed already in 1994, we can solve an important problem in number theory, which is factoring integers, and we can do that with an exponential speedup relative to the best available classical algorithm, which scales as 2 to the n to the 1/3, where n is the number of digits in the number that we wish to factor. Whereas the Shor algorithm does the same task of factoring in a time that scales only as n cubed. So that's essentially an exponential speedup. Only a couple years later, Love Grover came up with Grover's algorithm, which allows us to search a list or an unsorted list, like a reverse phone book search, where you're given the phone number and you're supposed to find the name. And he was able to show that an unsorted list of n items can be searched quadratically faster on a quantum computer than can be done with a classical computer. And this speedup is relative to the best possible classical algorithm. We don't yet know for sure that there isn't a better factoring algorithm, but in the case of Grover's algorithm, we know that this is best classical versus best possible quantum. There's a quadratic speedup that's guaranteed. A few years later, an algorithm was proposed for solving linear systems of equations. Very widespread problem, of course, with many applications, again with exponential speedup. Given a simple matrix equation, AX equals B, where A is a matrix, an n by n matrix with certain conditions being satisfied, it's possible to return the solution vector x in a time that scales as only order log n versus a low-order polynomial for the classical version. And then there are more exotic things which go back to the Feynman vision. For example, simulating quantum field theory is something that can be done with an exponential speedup as well on a quantum computer. And only yesterday, a new paper appeared on the archive, which seems like an extremely interesting and important result. An exponential speedup for semi-definite programming. And that is a very widespread optimization strategy. And these authors showed that if you are given n constraint matrices of dimension n and rank r, you can get an exponential speedup in the matrix dimension n compared to the best classical. So you can see that this field is generating surprises all the time. Who knows what will happen tomorrow? Perhaps we'll find another really amazing quantum speedup. All this leads to various quantum killer apps. Shor's algorithm allows us to break public key cryptography. So this has huge implications for cybersecurity. unrelated to quantum computing, but still in the domain of quantum information processing, we know that we can provide provably secure quantum encryption. It's guaranteed by the laws of quantum physics. And back to quantum computing, and again, the Feynman vision, it's possible to perform exponentially faster simulation of quantum mechanics, which we believe is going to lead to discovery and first principles design of novel materials, of pharmaceuticals, etc. And this will be done by solving the molecular electronic structure problem. This is illustrated in this recent experiment from the IBM group here. And then finally, perhaps not finally, another point, quantum speedups and optimization. This will have implications for machine learning, verification, validation, anomaly detection, supply chain and logistics, finance, topics that I believe will be discussed in some detail later today. Now, of course, this has been noticed by governments around the world. And already last year, the US government issued a report called Advancing Quantum Information Science, National Challenges and Opportunities, signed by the President of the United States, the previous president, I should say. The Europeans have invested €1 billion in the quantum technology flagship project. The Chinese, exactly a month ago, announced that they're building the world's biggest quantum research facility. And of course, it's not just governments, it's also companies like Fujitsu who have taken notice. And here's a quote from the CEO of Microsoft in his recently published book. He wrote, "The battle over quantum computing is an arms race as important as AI or virtual and augmented reality, though it has gone largely unnoticed." And of course, this event is going to change that perception. So what is the source of all this quantum power? This is a very hotly debated question. Researchers in the field are working on it all the time. We don't really know yet, but I think it is fair to say that it all started with the idea of the quantum superposition, which was immortalized by Schrödinger with his famous or infamous cat. The superposition principle tells us that objects can be in a superposition of two states that are orthogonal, like a cat that is dead and alive at the same time. And this is what we call a qubit. Any two-state system that can be in two states simultaneously, A times 0 plus B times 1. Now, in the early days of quantum mechanics, this was considered a mystery. There was a lot of philosophical discussion about the implications of the superposition principle, and it's still ongoing. But quantum information has taught us that we should embrace this phenomenon, very counterintuitive, not as a mystery, but rather as a useful resource. So how can we use this resource? Here's an illustration of a qubit versus what happens in the classical domain. Let's say that we wish to solve an optimization problem, which we heard about in the previous talk. The optimization problem is to find the global minimum on some energy landscape or some function with a shallow minimum and a deep global minimum. And of course, we don't know what this actually looks like. So one classical strategy that works well is called simulated annealing or random walk with gradient descent. And so if you let loose a classical particle, it starts over here, it starts to walk randomly, and every once in a while it goes uphill, as well as typically downhill, and it can go down the wrong way and end up in the local minimum as opposed to the global minimum. What does quantum mechanics do? Here is the same problem represented using qubits. So when the simulation starts over, you'll see that we start right now from a flat, uniform superposition, and the object that's being formed here is the quantum wave function. Here is the shallow well, the deep well is forming. The quantum wave function is initially localized in a shallow well, but then it tunnels across to the deep well, and eventually it's localized fully in the deep well, which is the solution. All this involves superposition, interference, cancellations, as well as tunneling. So this is some of the explanation for what the source of quantum power is. It's a very different solution strategy. Now, of course, there's bad news here as well, and this is what is called decoherence. It turns out that these quantum superpositions are very fragile. Every real quantum computer interacts with its environment. The environment is everything that is outside of the quantum computer. Now, unfortunately, this environment acts like an uncontrollable observer, much like the famous anthropologist who is making random measurements, so to speak, on an exotic tribe and modifying their behavior. Now, that happens in the quantum domain too. And if you start a quantum computer in a superposition of two states, and along comes a photon from somewhere, it interacts with the quantum superposition, destroys it, and leaves us with a boring single state, which is like a classical computer. And which of the two, by the way, is utterly random. So if you have a quantum computer that is too decohered, that's really bad news, because it turns out, this is a theorem, a sufficiently decoherent quantum computer can always be efficiently simulated on a classical computer. In that case, why bother? Why bother building a quantum computer? Well, fortunately, there is good news. There is a theory of quantum error correction, which is very elaborate and beautiful. Some of it was summarized in this book that was written by many authors several years ago. And the most important message about decoherence and quantum error correction is that decoherence is always going to be there. And if we don't do something about it via quantum error correction, we will never be able to scale up quantum computers. If there's one message I'd like to leave you with today, it is that everything you're going to hear today must be taken with that grain of salt, or that hope that we will be able to incorporate quantum error correction in order to make quantum computers robust. We know the theory for how to do it. It has to be done in order to build scalable quantum computers. OK, so I've talked a little bit about qubits, but what does a quantum computer really look like in real life? And I'd like to give you a representative sample from the examples that we will hear about today. So here is the D-Wave version of a quantum computer. It is actually what is called an adiabatic quantum computer, or a quantum annealer. It is a special purpose optimizer. It uses superconducting flux qubits, and D-Wave currently holds the world record for the number of qubits exceeding 2,000 in the latest generation of their devices. Here is the Google version. It doesn't use the adiabatic model. It uses the circuit model. And unlike the D-Wave machine, which is a special purpose optimizer, this is meant to become a universal quantum computer, universal meaning general purpose. It can compute any function. Also represented today is IBM. They too are striving to build a universal circuit model-based quantum computer. Rigetti will be here today as well. Again, a circuit model universal quantum computer. And all four of these use various types of superconducting qubits. IonQ is using trapped ions to build a circuit model universal quantum computer. So what unifies all of these, I think we can all agree, is that they're very unlike classical computers. The principle of operation is very different. How they look is very different. Their operating environment is very different. They all require dilution refrigerators that cool them down to millikelvin temperatures. At USC, I'd like to tell you a little bit about what we're doing. We have, thanks to the generosity of Lockheed Martin, a joint center with them, which houses a D-Wave machine. In fact, we've had 3 generations of the D-Wave machines over the past 6 years, starting in 2011. After we installed the first D-Wave chip, a couple of years later, Google, NASA also installed the D-Wave at NASA, not far from here at NASA Ames. Los Alamos National Lab did the same in 2016, and Temporal Defense Systems, Oak Ridge National Lab, and the University of Toronto all have access to D-Wave machines as well. Our current D-Wave machine is a 2X, the D-Wave 2X model with 1,098 qubits, and we're hoping to upgrade to the new 2000Q version soon. Now, we're also exploring other options. In fact, in partnership with IARPA, we have entered into a contract to lead this large group of institutions and 2 companies in order to build a new type of quantum annealer that will have 100 qubits, hopefully, within 5 years. We'll be using aluminum superconducting flux qubits. And similarly to D-Wave, our interest is in solving optimization and sampling problems. OK, so now let me talk about the impact of quantum computing. And I'd like to divide it into the short term, less than 5 years, and the longer term. So let me start by talking about factoring, which is, to many, the holy grail. And this is where it started with Shor's algorithm. Unfortunately, it looks like for factoring, we have a long road ahead. The state of the art, at least as of last year, 2016, this is Rainer Blott's group in Innsbruck, they were able to perform an extremely difficult experiment, which involved 5 calcium trapped ions. I know you can see 6 here, but that's because it's from a different experiment. And what the experiment did with factoring is to prove that 15 is 3 times 5. But only with 99% confidence. So this is where quantum factoring is today. In fact, it's a little bit of underselling it, because the number 143 has also been factored. But this was done using liquid state NMR technology. And we believe that liquid state NMR technology is non-scalable in the long run. So it was a feat of experimental prowess, but it's not clear that this method of doing things is going to take us further. So rather than factoring for the foreseeable, well, the near future, less than 5 years, we'd like to focus on more attainable near-term goals to see where the impact is. And I'd like to focus on 2 sub-goals, quantum simulation and this unholy phrase, quantum supremacy. Let's start with quantum simulation. This is back to the Feynman vision. We'd like to demonstrate an advantage in quantum simulation. So the goal is this. It is to demonstrate that a quantum computer performs a useful simulation task of another quantum system that is beyond the capability of any classical computer. So we'd like to use a quantum computer to simulate other quantum systems. And this is not far off. Here's one example. This is a real condensed matter physics problem. It's simulation of quantum magnetism, in this case using 10 trapped ions. And the problem that this quantum simulator of 10 trapped ions is supposed to solve is to probe the quantum phase transition from a paramagnet to an antiferromagnet in what is called a transverse field Ising model. So in a little bit more detail, here's a Hamiltonian. Think of it as a cost function. This is the transverse field. Its strength is B. This is the coupling term between the qubits. Its strength is parametrized by this number J0. And we expect that as we make the transverse field large compared to the coupling, the J0, so when the ratio B over J is large, like 5, the system will be paramagnetic, which means that there will be no correlations between the states of the ions. And indeed, this is what is observed. And by the way, this was carried out in Chris Monroe's lab already 4 years ago. So what you're seeing here is the correlation between ion number 1 and 2, 3, et cetera. So as a function of distance, correlation as a function of distance. And you see that indeed, when the transverse field dominates over the coupling, the correlation is essentially 0. But then when we flip it around and we make the coupling strong compared to the transverse field, so when B over J is small, what we expect to see is the antiferromagnetic phase where the ions are anti-correlated. And that is what we're seeing. When B over J is small, we see an anti-correlation that decays slowly over distance. So this is an example of simulating a quantum system, a very beautiful experiment. And the nice thing about this is that this becomes classically numerically intractable when we're talking about n is the number of qubits or number of ions, number of particles, greater than 40 or so. Now, this experiment used 10 ions. There's in principle no reason that it can't be scaled up to a larger number of ions. So this is very promising. We know that we can enter this classically numerically intractable regime by scaling up these types of experiments. And it has real impact. This idea of simulating quantum magnetism is undoubtedly going to lead us to the discovery of new materials, perhaps exotic materials. So I'm very hopeful about this field of quantum simulation. I think this is a great direction for the near future for quantum computing. Now, switching over to something a little bit more ambitious, quantum supremacy. So what is it that we mean when we say quantum supremacy? It's a very hot phrase nowadays. Look it up, and you'll get many hits. So quantum supremacy is this. It's to demonstrate that a quantum computer can perform a possibly useless task that is beyond the capability of a classical computer, of any classical computer. And the reason this is different from quantum simulation is because it is supplemented with a complexity theoretic assumption of the form, if you could perform this task efficiently on a classical computer, then something terrible would happen in computer science. What's called the polynomial hierarchy would collapse. So more colloquially, that's known as P equals NP. We would be able to solve NP problems that are considered very hard and probably don't have a polynomial time solution. We will nevertheless be able to solve them in polynomial time. It's believed to be not possible. But if one could demonstrate that a classical computer could perform this task assigned to a quantum computer under quantum supremacy, then the polynomial hierarchy would collapse. So in other words, whatever we're going to give the quantum computer will be extremely hard and extremely unlikely for a classical computer to be able to do efficiently. The reason this is different from the previous slide with quantum simulation is because for quantum simulation, we don't have this kind of complexity theoretic assumption underlying it. So why is this important, this idea of quantum supremacy? First of all, I would say it's foundational. Because if we could demonstrate quantum supremacy, it would refute the so-called extended Church-Turing thesis, which has prevailed for forever. And it states that classical computers can simulate any physical process, including quantum mechanics, with only polynomial overhead. If we could do quantum supremacy, this would be refuted. Also, it's practical, of great practical importance, because it would increase our confidence that quantum computers are on the right track. So let me give you a couple of examples of quantum supremacy ideas, proposals. Probably the first one is known as boson sampling. And this involves this type of problem. This is a linear optic circuit. The problem is, once you set up a random linear optic circuit, random in terms of the types of linear optical elements that are inside the circuit, the problem is to sample from the distribution of detections of these photons that propagate through the circuit. So sampling that distribution of detections of photon arrivals is estimated to be a hard classical problem. In fact, there's a paper from last year that estimated that for a certain variant of boson sampling, this problem is hard already for 7 photons. And tantalizingly, last year, there was an experiment that demonstrated boson sampling with 5 photons. So it looked like things were extremely close in terms of quantum supremacy. But very recently, a pessimistic paper appeared, which showed that these previous estimates actually didn't use the right classical tools to estimate the hardness of this problem. And with using better algorithms, better classical algorithms, it's become possible to simulate these boson sampling experiments for up to 50 photons or so. And therefore, any boson sampling experiment would have to use more than 50 photons with extremely stringent additional requirements, like low photon propagation in thousands of modes and high efficiency detectors and precise settings of millions of phase shifters. So while there is still hope for boson sampling, perhaps, at least the way we understand it right now, it may not be practical for demonstration in less than 5 years. OK, so if not boson sampling, how about random circuit sampling? This is the approach that's being pursued by Google. This, again, is their 9-qubit Gmon chip. And here the problem is formulated as follows. So imagine you have a chip. It doesn't look like this. Imagine you have a chip with qubits arranged in a square. Here it's 6 by 6, but Google is actually working on, apparently, on a 7 by 7 chip. So every circle here is a qubit. And let's say that at every time step, this is time step 1, and this is time step 2. At every time step, you apply 2-qubit gates and random single-qubit gates. And then at the next time step, you apply a different set of 2-qubit gates and new random 1-qubit gates. And then you evolve this for maybe 100 steps or so, maybe more. The problem then is to sample from the distribution of strings, classical bit strings, that are output by this circuit. You get a random classical bit string when you make a measurement at the end of this computation. So that distribution, it turns out that it's estimated to be hard to sample from, classically, for 50 qubits or so. And if you could do it efficiently, you would presumably collapse the polynomial hierarchy. So the Google experiment is on track. Just about a month ago, they released a paper showing that the 9-qubit Gmon experiment is working as it should. And they hope to reach 50 or so qubits and a demonstration of quantum supremacy in less than a year. And we can all hold our breaths and hope that they succeed. Now, I'd like to also briefly talk about what I think of as a partial quantum supremacy experiment, or perhaps more appropriately, a limited quantum speedup experiment that we performed with the latest generation of the D-Wave chips, thanks to D-Wave letting us use one of their machines in Burnaby. So here is that D-Wave 2000Q processor. It has up to 2,048 qubits. And what we tried to do, this is work with Tamim Al-Bash, was to solve this notorious NP-hard problem of finding the lowest energy spin configuration of a spin glass. So this is a disordered spin material. Finding the lowest energy configuration is extremely hard. It's NP-hard. That's been known for a long time. So what you're seeing here is the time it took the D-Wave machine to find a lowest energy configuration, the deepest valley in the hill that I showed earlier, as a function of problem size quantified in terms of this quantity L, where the number of qubits is actually 8 times L squared. The reason we pick L is because then we get nice linear scaling. Actually, this is exponential scaling because this is a log-lin plot. And what we were able to show is that for a carefully crafted set of problem instances, the D-Wave time to solution slope is better than the slope of simulated annealing, as well as another classical heuristic algorithm called spin vector Monte Carlo. And this is within the error bars. They're not shown, but this is 2 sigma error bars. So we are confident that the D-Wave processor outperforms simulated annealing and spin vector Monte Carlo on these problems that we've designed. So that's
That's really interesting because it gives us an inkling that there may be a speed up to be had with the D-Wave processors. However, I call it a partial or a limited demonstration because, as it turns out, if we use a different classical algorithm, not simulated annealing or spin vector Monte Carlo, if we use what we know of currently as the best classical algorithm, simulated quantum annealing, that's this green line here, as you can see easily with your naked eye, the slope is better than what we found on D-Wave. So this is an example where we have a speed up relative to a limited set of algorithms, classical algorithms, which are competitive. Simulated annealing is used all the time, everywhere. So it's an important algorithm to try to beat. But it's not an absolute speed up because we found another classical algorithm, very similarly to what happened with boson sampling, that does better. Still, we remain hopeful that we're on the right track here, and perhaps we will actually be able to eke out a real speed up as we keep probing. So as these three examples demonstrate, the race is on with quantum supremacy. And the important thing is that however it is achieved, we don't know yet how, perhaps it will be the Google version, quantum computation that exceeds the reach of classical computers is going to mark the beginning of a new era in quantum science. And I believe we're going to see this quantum supremacy demo in less than 5 years. I would bet some money on that. So that's for the short term. Now, what about the long term? Anyone have a crystal ball? I don't. So let's do crowdsourcing here. And let's ask PageRank. OK, so what do you think is going to happen if you pose this query to Google? Quantum computers will. You can try it for yourself in real time if you're online. Here's what you're going to see. That's the number one answer. Now, the number two answer. So this is pretty cool. I think they're right, okay? Because, of course, what's really going on is it's a superposition. All right? And now all we have to do is make the right measurement. When we make the right measurement, this will happen. OK, thank you. Sure. Yeah.
Hello. Oh, that was an excellent talk. I have a question. Do you see any possibility of evolving a new instruction set architecture to capture the glimpse of a future processor design that will accommodate this type of work?
So an instruction set architecture is something that people are working on. Microsoft has revealed a quantum programming language, which is maybe not exactly the same as RISC, but it is definitely something that is being thought about by various groups around the world. And so the answer is yes. It is not too early to start to think about quantum programming languages and RISC architectures. We need those in order to program quantum computers.
I'm looking at the analogy of quantum computing to just massively parallel Monte Carlo methods on classical computers. It seems like the same types of things are being done. Can you comment on how is a quantum computer really different from a computer made to optimize parallel Monte Carlo methods?
Yeah, so the answer to that is superposition. So if you use parallel classical processing, you're paying extra money for every additional processor that you put in the loop or that you have to buy. With quantum mechanics, we get that kind of parallelism for free, in a sense, by expanding the number of qubits rather than investing in a whole new processor every time. So quantum computing operates via a different principle. It operates via the superposition principle. Classical parallel computing operates by paying more money for every additional processor.
Well, not when your variables are really probabilities, and therefore the 32-bit floating point number I could represent, instead of 1 or 0, I could present any fraction of being on or being off at the same time.
Yeah, so of course, I'm not trying to give you a precise technical answer here. So if you recall the point I made about quantum decoherence, it actually applies also to what you just said. When you prepare a quantum superposition, when you make a measurement, if you're not careful, well, let me put it this way. When you make a measurement, you will collapse the superposition into a random state. You're going to get a random answer. So there's an art to designing quantum algorithms, which is to pick the right set of programming instructions, what we call unitary transformations, in order to create a superposition such that most of the probability mass is concentrated on the right answer. So when you make a measurement and collapse the superposition, one of the right answers will emerge. This is, for example, how Shor's algorithm works. And at the end of the day, it starts from a uniform superposition state and then transforms that uniform superposition into a different kind of superposition where most of the probability is located on the factors of the numbers that we're trying to find. And if that doesn't satisfy you, let's take it offline. Okay. Thanks. Thank you.
Okay, so we made it to our first break. So now let's take a break over in the Grand Hall. You'll have an opportunity to take a look at the 11 demos in the technology showcase. And then if everybody can come back here at 11 o'clock, our next panel session will be quantum computing hardware. So enjoy the networking break, everybody.